It might come as no surprise that the person who comes to the rescue and salvages this is Isaac Newton, of course. Isaac Newton's basic insight marks the division between the ancient world and the modern world, at least in terms of science. All right, following up on Kepler. Newton's insight was the laws of nature are the same everywhere. There's only one physical universe. What does that mean? It means that the ancient division between terrestrial and celestial bodies is incorrect. There's just the Earth. The Earth is one of many worlds, and all of them obey the same physical laws. Conditions might be different, so it might look the same everywhere, but things obey the same laws. More importantly, understanding how things move on Earth can tell us about motions in the heavens, and understanding motion in the heavens will tell us things about physics on Earth. In fact, most of Newton's motivation for the work on the three laws of motion and the invention of calculus came from his desire to understand planetary motions. Newton proposes something which is now called the law of universal gravitation, and he proposes it in the following form, at least in the modern telling we put it this way. Two point masses which have values m1 and m2, separated by some distance r, will each feel an attraction towards the center of the other with a magnitude given by that the F sub big G, the force of that gravitational attraction, is g m1 m2 all over r squared, where this G is called the universal gravitational constant. And as you might get from that kind of grandiose name, it's a physical constant that is everywhere the same in the universe. It's a number that doesn't change and is everywhere at all times the same. We'll talk about the value of G in a little bit. Right now, Newton didn't know its value. You don't need to know its value to understand a lot of things that go on in gravity, and measuring its value is non-trivial. So for now, we're going to put it off. Newton is basically, although he doesn't know he's saying it this way, he's basically laying out a level of the fundamental rules of space and time. He says, in the universe in which we live, gravity has this strength connecting different objects to it, and G measures that. Newton is proposing what's called an inverse square law, where the strength falls off as the square of the distance. If we travel twice as far out, we get 4 times weaker, because the 1 over 2 squared would be 1 over 4. He was motivated by comparison to optics, a thing that he invented, wherein the intensity of a light signal falls off as 1 over r squared. And he was arguing from the basic idea that there's some constant influence called gravity, and it spreads out in spheres, and so it's divided across the area of the sphere, and the area of a sphere grows as r squared. So he says the intensity must fall off as 1 over r squared because of the same amount of stuff over that area. That's the intensity. All right. There are some things Newton has called the shell theorems. Things in nature tend not to be point-like, duh, so Newton's law seems a bit useless. It depends on them being points, and they can't. He needed to add up the contributions of all the different point-like particles that do make up, say, the Earth. And to do so, he invented integral calculus, the other half of introductory calculus. Turns out to have lots of other uses, so mathematicians kind of loved it a lot. And in so doing, he discovered a couple of useful results. Outside of a uniform spherical collection of matter, gravity acts as if all that matter were at the center. So if I have a planet made of lots of stuff, this looks like a dot if I'm outside, looking from outside. I can treat a spherical distribution of matter as if it were a point. So he's already like, so there you go. I'm back into my law. Inside a spherical collection of matter, the only matter that is closer to you to the center than you counts. So if I have someone and you're inside the Earth, which is not a great place to be, but then anything that is closer to the center than you exerts gravity on you, but all the stuff that's outside, further outside than you, does not. So none of this stuff exerts a net gravitational force on you. It turns out what the calculus tells you is that all the little bits of mass in here have people on the other side of you pulling in such a strength so as to cancel out, so that only the stuff at the center, closer to the center than you, ends up counting. Now, in a practical sense, nearly all heavenly bodies are spheres because their local gravity pulls them into that shape. That's the shape that things want to attain, and only sometimes can they get far off from it. So the Earth is basically a sphere. Sure, there are a couple of mountains and little bumps and stuff, but they're very tiny compared to the size of the Earth because the Earth's gravity is pretty strong. So we can get a long way using just these two rules and Newtonian gravity. All right, so 5 satellites orbit the Earth and outside the atmosphere. Each has the mass and orbital radius listed. Draw a blue circle around things that are the satellite feels the greatest gravitational force, and red circle around things that have the least. So if we look here, this is our standard, and therefore we'll call that 1. And our force, remember, is going to be g, mass of the Earth, mass of the object, over the distance squared. So that's 1 unit. But when we get to this one, we have 1 unit m on top, but we have double the radius on the bottom, and doubling something and then squaring it is the same as making it 4 times as large. So this has a strength which is 1/4. On the other hand, c has twice the mass up here, but the same bottom, so that ends up making it only twice. D is a little bit more complicated. It has twice the effect for being twice the mass on top, but has 1/4 the effect for having twice the radius on bottom, so I have 2/4, which is 1/2 as much as the base unit. And then finally, we have 4 times the mass on the top, but we have double the mass squared, which is 4 times as much on the bottom. The 4/4 cancels. These turn out to actually be the same. So now we can look and say who's the strongest. C was the strongest. And who's the weakest? B was the weakest. And accidentally, we also discovered that A and E were the same. All right, how do we weigh the Earth? How do we get this value of universal G? Universal gravitation is easy to study among astronomical bodies, and for algebraic reasons, it proves difficult to separate the value of G. For instance, we could figure out G times mass of the Sun, or we could figure out G times mass of the Earth, but we couldn't easily figure out the mass of the Sun or the mass of the Earth on their own. In fact, it took well over a century, till about 1789, for anyone to even measure it reliably. This was a guy named Henry Cavendish. He did it by building 3 huge iron spheres and hanging 2 of them on a wire, a very precisely balanced wire. So we have, dumbbell of spheres here, and they're suspended from a rod that is on a very, very calibrated wire, a thin wire whose torsion is known. And then Cavendish brought in another sphere, kind of imagine out of the page, and it would attract both of them, but it would attract the nearer one a lot more, and it would twist the wire. And by measuring the twist in the wire, you would, in principle, be able to figure out the force that was exerted, and if you knew the mass of the iron balls by, say, weighing them, then you could figure out what big G is. It was an insane kind of experiment. It was the Apollo moonshot of 1789, but it worked, and it got us a good value of G that we've improved a little bit in the intervening times, so that we now know that big G is equal to 6.67 times 10 to the minus 11, and its units are Newton meter squared per kilogram squared. These units have no particular physical, you can't say, oh, of course it would be newtons per kilogram squared. They're what we need to make the force law come out to be newtons, because this cancels out the r squared on the bottom, and this cancels out both factors of the mass on the top. So there's nothing very deep going on here. This is the units that you would need to get newtons at the end. This is an interesting number, though, and we'll talk about it. I'm not going to walk through this video, but I'm going to post a link to it. It's an excruciating 15-minute long thing at a time lapse, wherein this brave and dedicated, or perhaps demented, physics teacher repeats the Cavendish experiment and is able to show that things like walking across his physics lab floor can distort the readings that come out. It ends up proving excruciatingly hard to do the Cavendish experiment with any kind of reliability. He'll go, if you want to watch the video, he goes through and shows all the things he thought of. Like, he came in on a Saturday, so there's no one else in the building to create air currents, because when he did it when people were in the building, just the opening and closing of doors created enough air currents to slowly twist the 2 dumbbell things, and so he couldn't get a measure. And even after all that, it was pretty rough. So I'm not going to walk through the whole video. It is 15 minutes of it's not particularly excellent fun to watch a guy setting up this experiment. But if you're interested, I'll put a link. And it definitely brings home how impressive Cavendish was to do all of this in 1789, because it's even hard now when we have lasers and computers and stuff. All right, let's say that Alice and Charlene each mass 50 kilograms, and they're standing about 2 meters apart. The law of universal gravitation would say that they would each attract each other, and they would feel a force, which we can get by plugging into the formula. remember that this is going to be G m1 m2 over r squared. If you grind all that in a calculator, you end up getting this number, which turns out to be 41 micronewtons. Right? Remember, they are human scaled things, 50 kilograms each. We get a force between them, which is only 50 micronewtons, 50 or 40 millionths of a newton. All right, it's completely negligible in everyday life. The force of breeze from air conditioning would easily be 1,000 times larger. People walking through the hall or a truck going by outside would exert bigger forces on them than their mutual gravitational attraction. Why? Because G is so ludicrously small. Indeed, to get real forces, to get Newton-level forces, we need at least one of these masses to be very, very large to balance out the fact that the gravitational universal constant is so ridiculously small. Let's talk about where little g comes from. Consider an object of mass m on the surface of the Earth, which is a more or less uniform sphere whose mass we can measure as 5.97 times 10 to the 24 kilograms, and whose radius is 6.4 times 10 to the 6 meters. This is known geometrically and has been for hundreds of years. This requires the Cavendish experiment or something similar to get the value of g, and then it's pretty easy to get this. And up until now, we've said that the Earth will attract that object with a force which is just its weight. F sub little g is m times that little g. But Isaac Newton says the object attracts the force with a force which is given by universal gravitation, F sub big G, which is universal constant G times the mass of the Earth times the mass of the object over the radius of the Earth squared. Because how far is it from the center of the Earth? Well, it's on the Earth, so it's one Earth radius away. But really, these are the same thing. There's only one force. These are just two different ways of talking about it. So it must be that mg equals all of this. So we can cancel out the little m's, and we get that our freefall constant is the universal gravitational constant times the mass of the Earth over the radius of the Earth squared. If you actually plug in the numbers, you get not 9.8, but 9.72 meters per second square. That's about a 1% variation from what we would expect, and it comes mostly from the fact that the Earth is not actually uniform. We're also not exactly 1 Earth radius away, what that even means. Also, most mentions of g would include the spinning of the Earth, which throws off the number a little bit more. So when we do freefall constants in the classroom, we wouldn't have deducted the value that comes from the centripetal force of the Earth, and so it'd be a little bit off too. So this is respectably close. 1% is not so bad. That gives us a couple of takeaways. For most human endeavors, the height of the Earth is much less than the radius of the Earth. Even the highest mountaintop is only about 10,000 meters tall, which is not much compared to the 6.4 million meters that is the radius of the Earth. That's why it appears that the freefall constant doesn't vary from place to place. It varies, but it's out in the third or fourth decimal place where you're not going to really see it. We notice that the mass of the object drops out, as we'd expect, and therefore everything accelerates at the same rate, so we retroactively justify the Galilean result. And we can use the same thing to find the surface gravity of any astronomical body just by replacing the g, the m, and the r with the mass and radius of the planet you're talking about. For example, the mass of Mars turns out to be 6.39 times 10 to the 29 kilograms. Sorry, that can't be right. In fact, it's not. It's 23. Mars is less massive than the Earth, not more. And its radius is 3.39 times 10 to the 6 meters. So on the surface of Mars, things fall with a free fall acceleration, uniform acceleration, which turns out to be about 3.71 meters per second square. This is about 4/10 of g, a little bit less. So things on Mars would fall noticeably smaller, though certainly faster than on the Moon, which turns out to have only about 1/6 of g. Here we have 5 hypothetical planets that have mass and radii as shown, and I'm going to draw a blue circle around planets that have the greatest surface gravity, and a red circle around planets that have the lowest. Remember, as you're working, that the surface gravity is going to be universal g, which is not important here, mass of the planet over the radius of the planet squared. So again, if we take this as our reference value of 1, in B we have doubled the top, but done nothing to the bottom, so this would be twice as large. In C, we have done nothing to the top, but we've made the bottom 4 times larger, but then we square it, so it's really 1/16. In D, we have made the top 4 times bigger, but we made the bottom twice as large, and then we square it, which is 4 times the strength. So I have 4 over 4. This is going to be the same as A. And then in here we have 4 times the mass, but we have 4 times the radius and then squared or 16th, so 4 over 16th or 1/4 as much. So we can see that B is the largest and C is the least. And we can also see that A equals D. So it's a little counterintuitive to a lot of people that the bigger planet doesn't necessarily have a stronger gravity. Here it has, in fact, less gravity than the Earth, even though it has more mass. And people like to think that large radius would give you more gravity, but that's because things have roughly the same density, so having more of them, a bigger radius, would mean that you'd have more stuff. Your m would go up as the cube. In fact, if we look at this, we would say if your density is constant, then this is something like the density times the volume, which is 4/3 pi r cubed, and we have r squared on the bottom. So we see in the case of constant density that g is proportional to the radius of the planet. But things wouldn't have constant density. If you made something 2 or 3 times the radius of the Earth and you tried to pack it with stuff as dense as the Earth, it would actually melt and flow. It would be too much pressure on it and it would become molten and flow down. In fact, the Earth is not constant density for exactly the same reason. So our intuition of just bigger things should have more gravity has an assumption built into it that is physically not very common.